In this section, we are looking at acceleration due to gravity. So all the videos will be related to this, and the variations and everything I'll be discussing in this video itself. So it would be one big bunch of videos, but talking about one thing, that is acceleration due to gravity. So acceleration due to gravity is the rate of acceleration, I'm reading over here, experienced by any object falling freely near the surface of a planet, assuming air resistance is negligible. It is caused entirely by the planet's gravitational pull. So basically we are talking about free fall. So what we have here is a planet. It can be, and we have an object falling towards the planet. So the rate at which it gets accelerated, the rate at which the value of the velocity changes, that is nothing but your acceleration due to gravity, denoted by small g. Right? Now, here we are ignoring the air resistance. And what else? It is basically under free fall. Right? So let's look at the mathematical expression. See, any given object will experience a force of, because of the planet, mass of the object divided by the distance from the center of the planet. So here mp is your mass of the planet. Then mass of object. R is the distance from the center to the object's center. So distance between the centers. So we also know that force, we can figure out force with this formula as well, where g is your acceleration due to that planet's gravity. Acceleration due to gravity. So from above two equations, what can we conclude? So from above two equation, what we have is g mp. Oh, sorry, by the way, this is mo, mass of the object, mp, and then mo by r square will be equal to, and should be equal to, mog. So basically mo gets cancelled. So acceleration due to gravity can be figured out with this relationship. So what we can observe over here is that if you have an elephant, or a rock falling towards a given planet, the acceleration will remain same for both. So you can see that the m naught term is not there. So m naught is missing, as m naught is missing. So this, you guys can have a web search and have a look at a video wherein you have a bowling ball and a feather. It is left from a particular height in a vacuum chamber. It's a real video, it's not an AI video or something. It's a real video, and you can watch that, wherein both of this object, how it falls. I want you guys to watch that. Okay, so that is your acceleration due to gravity. So we are going to understand this in detail. There's a lot of variation over here. So let me actually also talk about the variation. So what variation are we looking at? Variation of G's expression. So one is we are going to talk about here, that is above the surface, far above the surface. Given a planet, we are going to talk about somewhere below the surface. So what we're looking at is how the value of G varies above the surface, below the surface, if it varies, and by how much. Mathematical expression is what we are trying to figure out. Then not only that, G on the surface, also on the surface. So we're looking on the surface as well. And yeah, and also how G varies. How G varies because of the shape of the Earth. It's not exactly that, but is exaggerated version of Earth shape. So shape of the Earth. Then because of the rotation also plays a role in value of G. So the rotational part as well. So even the rotational part. Rotation also plays a role of Earth. Then what else we'll see? So this is in general, this is specific to Earth. Actually, this is also can be understood in general. And with latitude. So, and with latitude. So I think I've covered all the versions. Anyways, just an overview. And with latitude. Okay, so how it changes, how G changes with all of these factors is what we're going to look at. So we have around 1, 2. We have, say, 1, 2, 3, 4, 5, and 6 variations of the expression for G. Okay. Right. So again, what we are looking at is, and you guys can understand why this is important. All our satellites are, launching of satellites can happen with this understanding. Then we can launch satellites to other planets also, as in artificial satellites. And for all of that, for the satellites to stay in orbit, we need to understand this, and that's why there's a specific set of videos and specific set of topics, set of text for this itself. So we are looking at acceleration due to gravity. Acceleration due to gravity is the rate of acceleration experienced by any object falling freely near the surface of a given planet. So we will be ignoring air resistance. So this fall is caused entirely by gravitational pull. There's no other booster or turbine or turbine per se, but there's nothing else pushing it below or pulling it below. So this is your math, and this is a set of variation that you will see. There's a lot of other observation that you get to see, but yeah, I'm not going to explain that now.